-5, difference of two squares. This is Algebra 1, Chapter 5, binomials. So we're going to start by multiplying binomials. And then what I like is they're going to now start introducing, can you recognize when a expression is a byproduct of the product of two binomials, two special cases. So these are special cases because we should notice something interesting about these two binomials. They are what we call conjugates. Conjugates are identical with different signs. So what does that do? Well, if we do FOIL, first is a times a, outer is a times -3, inner is 3 times a, and lasts are 3 times -3. So I'm going to make that all a little bit smaller so we can, so we don't run out of space real quickly. So first becomes a squared, outside is -3a, inside is +3a, and last is -9. Notice about our outside and insides, because they are conjugates, they produce opposites, -3a and +3a, and they cancel. And we're left with our first and our last. And these are perfect squares. Why are they perfect squares? Well, because conjugates are identical except for different signs. So our firsts are always going to be a square. Our second's going to be squared, but it's going to be opposite signs. So any number times itself is going to produce a perfect square with a negative as its first. So, and I hate how number 2, I mean, it's number 2 frustrates me. This is probably not the best number 2 to start off with. That would give us 16 minus x squared. If we square the first, or multiply the first and multiply the last. Remember, our outside and insides are going to cancel because we get 4x and -4x, so we won't have 3 terms. Our solution, our answer, is always going to be a binomial. And I would have done it in this manner, but so be it. I'm not going to be a stickler. They do it for both of them. So this is x squared minus 25. And notice what it produces. It's the difference, that's a horrible D, difference of two squares. Squares. X squared is a perfect square. 25 is a perfect square. It's the difference of two perfect squares. So very interesting. 81 minus x squared. That's how we can do these super fast. And so we get 25a squared minus 4. I don't have to worry about the outside and inside. Those are going to cancel every single time when we multiply conjugates. So I'm just multiplying the firsts, which ends up being 5a quantity squared, and I'm going to multiply the lasts, which is 2 times -2, which is still 2 squared, but it's going to be the subtraction of it because I know that my signs are going to be opposite of each other. That's 49a squared minus 4. So we can do these that fast. 16 minus 9x squared, I would rewrite it in standard form. 36 minus 25x squared, I would rewrite it in standard form. So these are super easy. I keep saying super easy, don't I? I say that quite a bit. Because if you take the time to figure these out and see the patterns, we can see how simple it is. And we have to recognize some of the things. Recognition, one of those recognitions are that those are conjugates, that they're identical with different signs. What is the process? That process becomes repeatable and retainable. Retention, we retain that information through repetition. Now, let's see what here. So just because we introduce a variable as our second term, Doesn't change anything. We're still going to multiply the firsts, which is 9x squared, and we're still going to multiply the lasts, which is negative 16y squared. Positive 4 times negative 4 is always going to produce a negative. This will always be a difference because we're multiplying signs that are opposite of each other, produce negative numbers or negative signs. So this is 4u squared minus v squared. So no more challenging. X to the fourth minus 64y squared. X to the fourth minus 9y to the fourth. You should be able to look at these. 4a to the fourth minus 25b to the fourth. Can you do it that fast? A squared b squared. Woohoo! Did you notice that ab times ab is a squared b squared? It's not 2ab. We're not adding, we're multiplying. And then this is going to be negative 4c squared. That's a good one. That's a good tester. Now I like this. This kind of shows how we can utilize this in real world math. So instead of trying to think about what 16 times 24 is, can I create conjugates? Can I do 20 minus 4 and 20 plus 4? 20 minus 4 is 16, 20 plus 4. And why is this easier? Well, because these are conjugates. Notice these are conjugates. So we're going to square the firsts. 20 times 20 is 400. And we don't have to worry about the outside and inside because those are going to cancel. That would be 80 and negative 80. And then we multiply the lasts. Negative 4 times 4 is negative 16. And then I can mentally subtract those. I know that that's 384, so I was able to multiply 16 times 24 without a calculator. So this is 30 minus 3. This is 30 plus 3. That's going to give me 900. This is going to give me minus 9, 891. I just multiplied 27 times 33 mentally in 4 seconds. That's not bad. I think that's very doable. 53 is 50 plus 3. 47 is 50 minus 3. Now, they must be conjugates. When you create these two binomials, they have to be identical except for the signs. So you're just not picking any two numbers. You do have to do some thinking to see what number plus and what number minus will create those. That same number minus will create those two numbers. So that's 2,500 minus 9, which is 2,491. That's going to be 40 minus 5, 40 plus 5. That's going to be 1,600 minus 25, which is 1,575. I think it's pretty impressive. I think it's really cool. 40 plus 1, 40 minus 1, 1,600 minus 1, 1,599. 90 plus 2, 90 minus 2, 8,100 minus 4, 8,096. 100 plus 4, 100 minus 4. That is going to be 4 zeros, 10,000 minus 16, which is 9,984. Ooh, I like this. So this is 100 minus 40, 100 plus 40. So that's, again, 10,000. And that's minus 1,600. We're going to subtract that. That's going to be 8400. Had to think about it. All right, now we're going to reverse the product. Can you factor? We are factoring. All we're doing is turning this addition and subtraction into a product of two things. So I see that some of the characteristics, the criteria, is it the difference of squares. Is it the difference of squares? It has three things. First thing is two terms. Is it two terms? Is it subtraction? And are both perfect squares? If that is the case, then it is a byproduct of conjugates. So two terms, 1, 2, subtraction, perfect square, yes. So we're going to take the square root of this, which is b, that will be my first, and we're going to take the square root of 16, which is 4, and remember conjugates need to have opposite signs. So two terms, yes, subtraction, yes, perfect square, yes, f minus 9, f plus 9. Yeah, see there's two terms because our outside and inside cancels, hence why there's only two terms. So 6 minus x, 6 plus x, I would rewrite it, negative x plus 6, x plus 6. I don't like this. I would have factored out a negative, and I would have had, this is my final answer. That's kind of technical. It's more high schooly than anything. Oh, I like this. Two terms, yes. Subtraction, yes. Perfect square, yeah. That's 3e. 16 is 4, and then the signs have to be different. 7n minus 1, 7n plus 1. So easy. Two terms, both perfect squares, yes. Both subtraction, yes. It's the difference of two perfect squares. So we take the square root of the first to get the first. We take the square root of the last to get the last, and then we have opposite signs. I like this. A squared minus 6, a squared plus 6. That's a good one. That's going to be 7b minus 4c, 7b plus 4c. I like that. That's a good, tricky. Both perfect squares, yes. 10 minus 11r, 10 plus 11r. I'd rewrite it, negative 11r plus 10, 11r plus 10. Notice these don't look like conjugates because they have the same sign. And they aren't because my first term is negative. So I would factor out a negative. And now guess what? Now they look like conjugates, don't they? Yep, because I had to factor out that negative. So again, here is 11 minus y, 11 plus y. I'd rewrite it in standard form, and then I'd factor out that negative. My first term tends to be, there's a lot of people who want it to be positive, so we factor out that negative. 5u minus 6, 5u plus 6. And it's this fast. 16, we should recognize our perfect squares. 15 and 4x plus 15. We should know most of them. Yeah, there you go. All right, that's a fast one. Recognizing those will be really important, especially when we start factoring, which is a very integral part of Algebra 1. We talk about it, A times C, special cases. These are all special cases when we get into the factoring. The difference of squares is one of the two special cases. Section 5.6 will be binomial squares, where we should recognize those things.